same?
Voltage.
Voltage. So the voltage across this one has to be the voltage across this one. So in this case, V1 equals V2. V1 equals V2. And so V1 is V1 is Q1 over C1. So Q1 is 2.70 microfarads divided by, wait a minute, sorry,
Other way.
150 microcoulombs, there we go, divided by 2.70 microfarads. Now notice in this case I kept the unit of microfarads and microcoulombs. Usually when I work these capacitor problems and I've only got one micro flying around, I'll keep it. Reason why is because in this case the micros just cancel. Remember, they're just factors of 10 to the negative 6. So they cancel out. And so what's 150 divided by 2.7? Might even go evenly, I don't know. Okay, 55.5. Okay, 55.5 or 55.6, I guess, right? 55.6 volts. Okay? So now that we know that this has 55.6 volts on it, I know that C2 has to have 55.6 volts. So this has to have 55.6 volts. Did everybody see that one? Okay. All right, now, how about the charge on this? Well, let's see. These two together are in, with this.
Series.
So these two together are in series with this one. And so therefore the charge here has to be equal to the charge here, which is both of them together. So both of these together have to have the same charge as this. So if this has 450, that has 150, what does C2 have to have? 300. And so then we can figure out what C2 is, because I have the charge and I have the voltage. So C2 is equal to Q2 times, divided by V2, yeah. Okay. Q2 is 300 microcoulombs. V2 is 55.6 volts. And so what would C2 be? Yeah. 5.4. Okay. 5.4 microfarads. Okay, so everybody see how I did that?
No, where did you get 300 microphones for C2?
Because this has to have the same charge as this combination. For the combination, you add the two charges together to get the total charge. So these two total charges have to be the 450. Okay? All right. For the C3, I already have the charge on. I just need voltage. How would I get the voltage?
Subtract the voltage you have on the left from the total.
Yeah, subtract the voltage I have here from the total voltage. Total voltage is 100. So V3 is VAB minus V12. And the reason why I call it V12 is because V1 and V2 are the same. You don't have to use my same subscripts as long as you know what you're doing. So in this case, V3 VAB is 100 minus 55.6. And so what you get is 44.4. Now that we have V3, I can calculate C3. C3, Q3 over V3, 450 microcoulombs divided by 44.4. So please do that and tell me what you get. What? 10.1? 10.1? Okay. People are nodding, so yes. 10.1. Make sure you keep the micro.
Can you do the one right before this, number 49?
Sure. Unless it looks so similar. Okay. All right, so it says a 25 microfarad capacitor is charged to a potential difference of 900 volts. The terminals of the charged capacitor are then connected to those of an uncharged 8 microfarad capacitor. Then it says compute the original charge of the system, and then compute the final potential difference across the capacitor, and then compute the final energy of the system, and we can compute the energy decrease when the capacitors are connected. Okay, so instead of just doing that one calculation, why don't we do the whole calculation for the initial part? So we're going to calculate we know what the voltage is, we know what the charge is, we can calculate the charge, and we'll calculate the energy stored on that capacitor. So what happens is I connect this to a potential difference of 900 volts. Okay, so I have 900 volts here, and it is a 25 microfarad capacitor. And so the first thing I want to do is I want to calculate the charge on it. And this is before. Okay, this is before. The charge on it before. Well, if I go back to my definition of capacitance and solve for the charge, I get Q equals C times V. C is 25 microfarads. V is 900 volts. So what do we get? Lots of charge. Well, not really that much charge. It's still micros, but we'll go ahead and keep the thousands of micros instead of changing it in mils, okay? 72,500. 22,500 microcoulombs, like that? All right. Now, there's one thing that they don't tell you. They then disconnect this from the 900 volts, okay, before connecting it to the other one. Because if they just connected it to the other one, then the other one would just get 900 volts, and that would be that. You know, you wouldn't get your charge from the capacitor. You get it from the battery. Everything would have 900 volts, and everybody would be happy. Okay? But that's not the way it happens. What we do is we then take this capacitor, okay, with its positive Q and negative Q over here, 25 microfarads, and we connect it to the ends of an uncharged 8 microfarad capacitor. And then the charge redistributes. The charge redistributes on the two of them. Okay? Because why stay here when I could go over to this plate? This plate has no charge on it. So I can still get close to the other side if I just go over to this one. Everybody see that? And this plate, I go over to this one. So what we want to do now is we want to use the principles involved for the redistributed charge. So let me draw a picture with it redistributed. So now I've got the 25 microfarad capacitor and an 8 microfarad capacitor. And so this charge is going to redistribute. So this is going to have a plus, I'll call it little q1 on it. Minus q1, that's over here. Plus q2, minus q2. I use little letter q instead of big letter q, just so you realize, that it's not the same q as before. All right, now, two principles. What configuration is this? Let me, in fact, just give you a hint. I'm going to draw 2 points A and B.
Parallel.
A and B, okay? So in this case, those 2 points are what? It's
Parallel.
parallel. So they're parallel to each other. So what do I know about that? Parallel. So what is the voltage has to be the same. So that new voltage up there at the top has to be the same as the new voltage down here at the bottom. Okay, so I have that.
Is that the 900?
No, that is not the 900 because we didn't keep the battery connected. We did not keep the battery connected. Like I said, if we kept the battery connected, then this problem just becomes silly. It's just this one, gee.
Why is your E all fancy?
Oh, just because I drew cursive cues, I figured I'd draw fancy.
I thought this was like a different type of.
Yeah, these are Q's, these are V's. Those are cursive cues. The art of cursive writing, that thing that was lost, that lost art. All right, now, so we can do this because this what we have is we have Q1 over C1, and C1 is 25 microfarads, has to equal Q2 divided by 8 microfarads. So we can solve for O. Well, I can, not just yet. I've got one equation, I've got two unknowns. Okay? I've got one equation and two unknowns. Before it redistributes, how much charge is stored here? 22,500 microcoulombs. Everybody see that? Before it redistributes, 22,500 microcoulombs is stored in there. After it redistributes, how much charge is stored? Same amount. And here's why. There's nowhere for it to get any other charge. Once you disconnect the capacitor from a battery, the charge it has is a charge that no more charge can go there. So this charge can redistribute, but you can't add any or take any off. So what that tells us is that, well, the charge that I have on Q1 plus the charge I have on Q2 has to be 22,500 microcoulombs. Okay? So I know that Q1 plus Q2 must equal 22,500 microcoulombs. Two equations, two unknowns, I'm going to solve. Let's simplify a little bit here. I can divide out the microfarads here, so I don't have to look at that. So Q1 over 25 equals Q2 over 8. I can solve this for Q1. Q1 equals 123.125. I'm pulling this up here. 25 divided by 8.
Yeah.
3.125?
Yeah.
Okay, so it's 3.125 times Q2. So now I can plug this back into here. 3.125 Q2 plus Q2 equals 22,500. What's this? 4.125. So if I take this and divide it Q2, how much is Q2?
$54.
54.
0.5.
54.
0.5.
And then Q1 is
That minus.
20,000 minus this.
$17,046.
Sounds good enough. If I put those things in here, it'd probably say, oh, you rounded wrong or whatever, but you know. All right, so far so good. All right, so now what you want to do is you want to calculate the voltage across each of these. So to do that, what you do is you just say that, okay, V, either one will work. Do you want to use the 25 or the 8? Doesn't matter to me. Okay, so V1, which by the way is equal to V2, oh, sorry. V1, which by the way is equal to V2, is equal to our Q1, which is 17,046 microcoulombs, divided by 25 microfarads. How much voltage is across that? A lot, yes. Question, is it more or less than 900?
Less.
It has to be less, because this was 900 with all of that charge on it. All of that charge is no longer on this. The voltage across must be less.
681.
681. Do I have confirmation on 681 here?
Yep.
Okay, so now I got my voltage is 681. 681 volts. All right, so now it wants the final energy of the system, and it wants a change in energy, so we have to calculate the initial energy of the system. Okay? Okay, so energy initial is equal to 1/2 Q V. And that's the initial energy. In this case, go ahead and take the micro and make it 10 to the negative 6 because it's going to get so big we're practically into there. So it's 1/2 times 900 times 22,500 times 10 to the negative 6. What do you get when you do that?
That's just the V squared, or?
Not in this one. It's 1/2 CV squared. And 1/2 Q squared over C.
That's what.
But this is the regular QV. That's why I like remembering this one. I don't have to worry. And then I can always plug in with my capacitance definition for the other ones.
10.12.
10.12? 10.12? Yeah, and that's just joules. All right, so now the final, couldn't resist, people. Is 1/2 multiplied by the Q multiplied by the voltage. See, in this case, we don't have to because we still know that it's the same charge because it's the same total charge stored and the total voltage. So we can use the total voltage that we calculated and the charge. So it's 1/2 the Q total, which is still the Q, multiplied by now my V, like Because the total charge stored did not change, the voltage did. So in this case, it's 1/2, 681, 2,500. So what'd you get for the final energy?
7.66.
7.66 joules. Okay? And so if you're wondering where the energy went, in this case it's a little simple. Because the energy went, because here's a lot of energy stored. But remember, when anything spontaneous happens, there's a loss of energy. So in other words, these spontaneously moved down here because this place has lower energy, because there was nothing on here. So these planes spontaneously moved down here, and so they used some of their energy to move down to the other plate. And that's where the energy went. So it took energy to move them from here to here, and that energy was used up. That's where it went. Yes?
That energy that we turned to heat, basically?
Well, that's a little complicated, but yeah, in a sense. I mean, they move down here and then they have to stop, and it's kind of when they stop that you can
Question?
Yes.
So if you add another capacitor to that, the voltage would drop more, but the
Yes.
charge would stay the
The
same?
total charge on all of it would stay the same, yes. Yeah. So in other words, what I did when I did that thing with the last problem was I treated this like an equivalent capacitor, which was the easiest way to do it. I mean, I could calculate each individual thing, but then I would just ended up adding them up, and it would be the same thing anyway. Did you have one where you inserted dielectric into a thing?
You have one where you take one.
Take one out, and that was the last one, right? Good, give me that one. That's what I'm going to do. Let's see. No, that's not the last one, is it? No, that's not that one. Let me see. Let me see if I can find it. 84?
No, don't listen to me.
Is this one here in the presence of a dielectric?
I think so.
It's one where you do things and you take out the thing. Ah, there it is. Yes. Okay, good. I found it. This is it.
Oh, your email just came.
Yeah, I know. This is the delay. Okay, here we go. A dielectric filled parallel plate capacitor has a plate area of 30 centimeters squared. Wow, that's pretty big, actually. Plate separation of 10 millimeters. That's 1 centimeter, by the way. And dielectric constant K equals 5. Capacitor is connected to a battery that creates a constant voltage V equals 15 volts. Throughout the problem, use epsilon naught equals
10 millimeters is not 1 centimeter.
10 millimeter is 1 centimeter.
Is it?
Yeah.
Yeah.
I have not had my coffee yet, so.
Okay, yeah. What I don't understand, it says throughout the problem use epsilon naught equals this. Why wouldn't you always use epsilon naught equals that? It's a constant.
I guess they're going by decimal precision. or
Nice.
something.
Find the energy of the filled dielectric capacitor. Express your answer numerically in joules. All right, so first of all, we have to calculate the capacitance of this thing. Let's do it. So the capacitance of this thing is kappa epsilon naught A over D. Now I have to be careful about this because it's tricky with units, especially when you're given units of centimeters squared. Because you want everything in meters and meters squared. So the tricky thing here is to convert that. So kappa is 5, that's no problem. It's our dielectric constant. Epsilon naught is our friend 8.85 times 10 to the negative 12. Area. Okay, 30 centimeters squared. I have to divide it by 100 and divide it by 100 again. So it's 30 times 10 to the negative 4 meters squared. 0.003. With the distance between the d, that's only a single power. I just have to divide it by 1,000 once, and that's 0.01. So somebody please calculate what the capacitance is. It's going to be something really small, but please calculate what it is. The answer is really small.
I think it's 1.32 times 10 to the negative 11.
Okay, so 1.32 times 10 to the negative 11.
To be more precise, it's 1.33.
Fair answer? No. All right. So then what we have to do, we want to calculate, we said it's the voltage is 15 volts. So V equals 15 volts. And the capacitance is, so the charge on this thing is the capacitance times voltage. So we have 15 volts times 1.32 times 10 to the negative 11.
1.99 times 10 to the negative 10.
1.99 times 10 to the negative 10. Coulombs. And if we calculate the energy, geez, it's going to be something really small. So 15 times 1.99 is 20, what, 9, 28 something?
2.98 times 10 to the negative 9. It's basically the charge multiplied by the voltage, right?
Mhm. Yes.
I was checking the capacitance in the first one next to the unit 9.
So negative 9. I don't know. I mean, did you plug it in? You did?
Yeah.
Did you make sure that was 10 to the negative 4?
For C,
0.01.
I just did it again.
Just make sure you got all your numbers. So I'm going to simplify the problem after this because there's principles that I want you to memorize. And the rest of the problem is a little tricky because you have to calculate that capacitance, that new capacitance when it's halfway out, blah, 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 and then it's all the way out. Okay, I'll leave that for you guys to do on your own. However, what I do want to discuss is what happens, what goes on with this. So let me just do a different problem here. I want to simplify my capacitance too. I like the problem, I just don't have time to discuss the whole problem. Too hectic. All right, so let's say I have a, let's make it simple. I have a 4 farad capacitor C, and I stick a dielectric in it, and the dielectric has a kappa of 3, okay? And I connect that to a battery of 5 volts. Okay? So when I have a kappa of 3 here, okay, what is my total capacitance of the thing? If it's a 4 farad capacitor and I stick a kappa of 3 in it, what is it?
Cool.
Go out here. We got a total of 12 farads. There we go. You start that. So now what happens here is that this stores its charge, and the charge here is 60 coulombs. A little bit unreasonable, but hey, what do you know? Okay, so we've got 60 coulombs of charge. Okay, now there's two scenarios I want to discuss. First scenario is I'm going to pull the dielectric out, as is. So I'm going to leave the battery connected and pull the dielectric out. Okay? So I leave the dielectric connected, I leave the battery connected, pull the dielectric out. So I end up with this. And I pull the dielectric out. Pull it out. So in this case, what happens is that the capacitance here drops to
40.
4 farads. Okay? And so what happens then to the charge on this thing?
It doesn't go back to the battery, does it?
The charge here ends up going back to the battery. The battery forces this to maintain 5 volts. So whether I'm inserting a capacitor or taking it out, if I leave it connected to the battery, that voltage has to be whatever the battery is. The battery will force it. It's a source of charge. So the charge on this would then be only 20 coulombs. Okay? Second scenario. I disconnect the battery and then pull the thing out. Disconnect the battery and then pull it out. Well, if I disconnect the battery and then pull it out, I end up with this. But in this case, where the capacitance once again has been reduced to 4 farads. However, in this case, the charge must stay the same. Has to. Must stay the same. So Q here is 60 coulombs.
And how does it hold on to that much of the charge when it's taking out the...
Yeah,
It
well,
has to. There's nowhere for it to go. It can't go anywhere.
the dialect doesn't take any with it.
No, because the dielectric is a polarized insulator thing. You're just pulling it out. So the voltage across, what's going to happen to the voltage across this thing?
Increase it?
It's going to increase when you pull that thing out. The voltage here is not going to be 5 volts, it's going to be 15 volts. If I look at the energy of this plate before, okay, here the energy was 1/2 QV. Q is 60 coulombs. The voltage V is 5 volts. So 60 times 5 is 300. I'd have 150 joules stored in this thing. I hope I did that right. Well, in this case, look at this. My energy here is 1/2 QV again, but now the Q is the same, but the V is 15 volts. Q is coulombs. And so this now is 450 joules. Where did the energy come from?
The charges are closer to each other. Because of the higher potential on this.
Let me ask you this question, right? Remember this dielectric, it's got little charges that have all those other charges there, right? Well, those charges are attracted to each other. It's going to take some kind of force to pull that out. That thing doesn't want to get out of there. It's okay if I've got some place for those charges to go. The charges just run off back to the battery. But if I don't, then you can't. So the work you put in pulling that out, that's where the energy is. Because there's work required for you to pull that thing out. Because that thing doesn't want to leave. Because there's little charges there that are attracted to the plates. And that's what happens to the little charges. They're basically fighting you all the way, so you have to put energy into it to pull that out. I wouldn't recommend it. Silly. But you get the idea. The principle, though, is this. If something is remaining connected to a battery, the voltage must, that battery is going to maintain a voltage. If it's disconnected, the charge must stay the same. It's got no place to go. So the voltage changes. Yes?
So if we switch the voltage, then will it get pushed out?
If you switch the voltage back this way,
Yeah.
flipper, then what would happen is it would just run off one plate and onto the other. That's what would happen.
Oh, okay. It
Yeah.
wouldn't like fly off.
No, it wouldn't fly. It'd go back. The battery reabsorb it.
Okay.
All right, so back to current events. Wow, we've got like 20 minutes. I'm glad I started early. But here we go. Okay, so last time what we brought up was we brought the definition of current. Charge flowing through time. Brought up current density, current per area. And we talked about in the microscopic view, the current density is equal to the concentration of charge carriers multiplied by the charge of each one, multiplied by their average drift velocity. Now, when we lump all this together, we start to say, well, okay, drift velocity is something that we can calculate it if we know other things, but usually what we do is we actually kind of look at the current overall first, as opposed to looking at the things that go into it. So in other words, what we do is you do experimental, you're looking at the current itself. You're not looking at the density of charge carriers and that. Usually what you do is you would use the current to measure that other stuff, to see what is the density, what is the drift velocity, what is those other things. That's what you would use. So what we do is we start out by saying, okay, there's a property in all of this stuff that determines how much or how little that this will be compared to the electric field that you try to put in. Okay? So in other words, if I try to put an electric field in here, I now want to relate that electric field directly to the current that I get. Directly to the current that I get. And so what we do is we define a quantity called resistivity. And it is done by the letter rho, resistivity. And a resistivity is basically a lump together of how much the atoms are going to resist that electric field when you stick it inside. How much that's going to slow down the current going in. So what happens is when I put an electric field the electric field inside of this thing, the current density that I get out is equal to the electric field divided by my resistivity. So this is kind of relating what current density I get out to the electric field I put in. The other way to look at this, if you solve it for electric field, which your book does, like doing it this way. There you go. Now the electric field doesn't cost a thing. Turnout doesn't cost anything. Yeah, but that's all nice and microscopic there. Let's turn to a macroscopic view. Let's grab a macroscopic view. I'm gonna go back to my mountain. Here's my mountain. Okay, here's my mountain. There we go. The height of that mountain is going to represent my voltage. Height of the mountain is represent my voltage. And I want to take a look at the amount of current that I get flowing down this mountain. Any amount of current. Current is going to be analogous to the river water. And so what we do is we say, okay. And to be honest with you, I am really surprised that they didn't just start out with this, but they just really wanted to go fancy like this or whatever. I really, this boggles my mind. So, your book's misleading at times. This is much simpler, okay? So anyway, I got the current flowing down here. And so what we want is we want the current that we get out of this thing. In other words, the current is going to be my dependent variable. Now when I apply a voltage to something, I'm applying electric field inside it. So that's how we're going to interpret voltages from now on. So in other words, if I take a voltage and put it across, on the inside I'm creating an electric field. That's what I'm doing. The electric field being the voltage divided by whatever distance I put that voltage across. So in other words, I'm introducing an electric field into the wire when I put a battery on it. And that's going to push current. So the question is if I increase the voltage, will I get more current or less current?
More.
Well, if I increase the voltage, right, I'm increasing this, so this is going to higher, this becomes more steeper. Is this water going to flow faster or slower?
Faster.
Faster, which means I get more current. So voltage is going to go in numerator. Now the other thing that we do is we say, okay, well there's this stuff with the resistivity in here because there's atoms and stuff in here, but on a macroscopic scale, we lump that all into one nice convenient quantity because we need to. And what that represents in terms of our little mountain thing is trees and bushes and rocks and the houses that are trying to avoid the mudslides and all that stuff. Okay. Those things get in the way. Okay. And we lump all that together. We lump all that stuff together, and we say that this stuff forms a quantity inside of a wire that is called resistance. That's called resistance. We represent resistance with the capital letter R. So, if I increase the number of shrubs and whatever on the hillsides, is the current going to go faster or slower?
Slower.
Slower. That's why they get all worried when it burns off, because there's very little there to avoid the current, and the current just comes rushing down and all of that. So what we do is we divide this by the resistance. There you go. Now there's a couple of other things about current that we have to remember. Current must flow in a complete loop. You cannot just have current going from one place to another and ending. Does not happen. Current has to flow in some kind of continuous loop. In this case, it goes down to the ocean, then you have evaporation, and then you have condensation. It's over here. Precipitation. I forgot how to spell it. And runoff. A complete circuit of water. Same thing with current. You must have something to complete the circuit, or it won't go. It'll stop. All right, so here's a question for you. Okay, so let's say that I've got my current running in the circuit here, and by the way, this is what we call Ohm's law. This is Ohm's law. Okay. Now we word this a little bit differently. The reason why I do it this way is the same way that I do Newton's second law when I introduce it. I introduce it conceptually. It's conceptually worth first with cause and effect. In other words, the force divided by the mass, that's acceleration. The acceleration is the effect, the force is the cause. Here, we are creating that current, we're causing the current with our voltage. We're causing the current with our voltage. So this is a cause and effect. But who likes to divide things? You know, when you can just simplify and multiply. So that's why most of the time you ever see Ohm's law is we see a voltage across a standard resistor or standard wire is equal to the current multiplied by the resistance. The resistance is giving a unit for which Ohm humbly called ohm. And so resistance has units of ohms, which is represented by a capital Greek letter omega.
Don't act like you wouldn't name the unit of something Collins.
I hate the last name.
Then Eric's.
I don't know, probably a name like George or something. By the way, that's a fancy omega. I figured if I was drawing fancy using these. Actually, that looks like hair or something. All right, so there we go. So this is Ohm's law. Okay, so this is what we talk about when we talk about the voltage across the resistor is the current multiplied by the resistance. Now we can go back and we can relate that resistivity to that resistance by using the geometry. So when I have a cylindrical wire in which the current flows from end to end, say the current's coming out of here, okay. The resistance of this wire is equal to the resistivity of the material multiplied by the length of the wire. Because if you think about it, if you're driving on the 405, right, and you had to drive longer on the 405, it's going to take you even longer to get from place to place.
Surface streets.
Divided by the area, the cross-sectional area. So the area is the cross-section area, in other words, perpendicular to the current flow, and the length is along the current flow. Okay. And the resistivity depends on the material and the temperature. The material and the temperature. I'm going to gloss over the temperature dependence generally, and the reason why I want to gloss over the temperature dependence is because it just is one extra layer of complication to this, which I tend not to go over. But do understand that that's what resistivity depends on. Don't tell me that resistivity depends on resistance and L over A. No, no, no. Remember, cause and effect. In other words, we make the wire out of this material with a certain resistivity. We make it a certain length and have a certain cross-sectional area. We're going to get that resistance out of it. Right now, this resistivity we can use to classify materials because different materials have different resistivities. And we can look at it, and basically it's how much this thing is going to resist current, how much this material resists the flow of current, how much this material requires a larger electric field to get the same current density out of it. Now the units of this are ohm meters, because notice ohm meters times meters divided by meters squared gives you ohms. So these resistivities are in ohm meters. And remember, resistivity is not resistance. They are two different things. Just like electric potential is not the same as electric potential energy. They are two different things. So you got to remember, these things, the little names, similar but not. Similar but not. All right, resistivities. Okay, so we got a couple of materials here. Silver. And these are resistivities at 20 degrees centigrade, which is room temperature. Resistivity 1.47 times 10 to the negative 8 ohm meters. Oh, okay. Now we've got a couple more. Aluminum. All right, here we go. 2.75 times 10 to the negative 8. Ohm meters. Okay? Oh, they got mercury. 95 times 10 to the negative 8. Probably wouldn't want to make too much stuff out of mercury at room temperature. It's a liquid, but you know, hey, there you go. Okay, well, that's not too bad. So your resistivities tend to be in the order of 10 to the negative 8. Okay? So just remember that resistivity. For example, let's see, glass has a resistivity of anywhere from 10 to the 10th to 10 to the 14th ohm meters, in the order of, oh wait. Oh, that's not in the order of 10 to the negative 8. That's 10, that's not a typo. This is anywhere from 10 to the positive 10 to 10 to the positive 14. Well, let's look a couple more now. Let's see, where's the first one to go? Oh, here it is. Quartz. 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 75 times 10 to the 16.
Never use them as a conductor.
Wow. Look at the differences here. Oh, amber. Amber. Let's try amber. Amber. 5 times 10 to the 14th. Oh. Oh dear. Well, that's why we have different types of material based on this. And it's not some subtle thing. It's not subtle, the differences. There's a grip that's in the order of 10 to the negative 8. And there's another grip in the order of 10 to the positive 10 and above. That's how much different materials have resistivities. Different materials. So, in other words, the ones with the low resistance up here,
Some metals.
electricity moves easily. We refer to these as conductors. Those are conductors. Now there's a few disclaimers that for people on flat. Now, for people on flat, there's a few disclaimers. You cannot use for your thing, nor of that mess in my house that has to blurt the word out, okay? I've got a 6-year-old. My house is messy. That's what happens. Especially when you can't keep up with them anymore. But if you want to talk to him and he wants to talk to you, that's perfectly fine. He loves attention from anybody and everybody. That's the way it is. You love attention too? All right. Yes, go ahead. Oh, I apologize. I did not finish grading the exams yet, so
How does it look so far?
probably next week. They still look good. They still look good. I'm surprised at some of the errors, and one of the things I have to do is go back and try to rearrange points, and that usually takes a while. Because when I get through some of them and I find out more people are missing this or less people are missing this thing than I thought, then I rearrange the points differently. And I have to go back and grade them all to make sure they're all consistent. Yes?
I forgot in calculator, how much is that going to affect my grade if I left everything as exact answers?
You mean like square root of 2 or whatever weird things like
Like
that?
sine of,
Oh dear. I'll figure it out.
I'll remember for the next one.
All right, so let's see. Let's take our Sunday lab. Lab.
Wait, did we have a Sunday block? Like an actual Sunday run block yesterday?
Yes, there was an up and running lab yesterday, but the problem was is I started it, like I said, I was sitting down, the Oscars were on, okay? I had papers I was grading, but other than that, I really wasn't doing anything. So, paying attention very little to the Oscars. My wife would call my attention to the TV once in a while because she liked somebody's dress or something. She wanted me to look at it.
Or if Leo won.
Fine, and Leo won, okay? And Spotlight, for some reason, a movie that I'd not really watched or heard of, won Best Picture.
Is that the one with the guy who played Bruce Banner in it?
I have no clue. It was? Oh, okay. So,
Yeah, it's
yeah.
about the Catholic priests raping kids.
Yeah. So anyway, I just wanted to know what time in the evening you guys want to do it. Can't do it too late because I got a kid, has to go to bed.
It's
Okay?
not mandatory though, is it?
No, it's not mandatory.
So we can't do it at midnight?
No, can't do it at midnight. So let's see, 6. So in other words, I want to schedule this now so that if I send out an email or send out that email and you don't get it for 2 hours, you still know it's there. Okay? So I could do it 6, 7, or 5. I could go earlier. I can't go later because I do it for 2 hours. You come in, you come out. It's kind of like an office hour type thing. And if nobody's there, I might walk away for a bit and come back. So in other words, it's not anything official. It's kind of like a tutoring session that you walk in and out of. Kind of like that. And you can ask me questions about homework. So when do you want it?
7 to 9.
No later than that.
7 to 9?
Yeah.
All right. All right. There you go. So we'll do this Sunday, 7 to 9. Okay. Just a little bit extra, you know. Last second stuff. Now, let's go to, and I apologize for the whole group problem last time. Whoops. No. Oh, I see. See, notice what happens if you do just a typo? Oh, I hate sites like that. You see what I mean? You do a typo, you left out the G, and it takes you some phishing website for, you know. You get it, right?
We get it, but we don't see.
Oh. Now, for those of you who might want to follow me on Twitter, most of my tweets are about reality TV. So I don't know how much you really would want to follow me, but you know. I'm very opinionated about them too. They're so silly.
Which one?
Oh, I Survivor, Big Brother. I'm even watching that Gran Hermano. It's Big Brother. It's the Big Brother on Telemundo. I can't understand any of it, but I watch it anyway. Yeah, I'm watching a Spanish Big Brother, you know, and I just.
You should stream yourself watching it. You're probably gonna.
I probably could stream myself watching. I don't understand this at all, but I'm watching this.
Just add your commentary.
Yeah, just add my commentary.
That would actually get a lot of views.
You know, the funny thing is I actually got retweeted by the host of that show. Could you imagine like Jeff Probst or Julie Chen retweeting you? No, I actually got retweeted by the host of
What
that
did
show.
you say?
Because I said I learned a new Spanish word, embaraza, as in Catalina et embaraza. Now, those of you who know embaraza, yes, one of the house guests was on the show, and yes. And I didn't know what it was. I was watching the show. I had no idea what they were talking about because she said she was sick. But then they gave her this thing, like this. It came in a little blue package. And then she went out and she came back in with this little thing. She was crying and then it said she es embaraza. And I thought, I know what that is. So I didn't have to know any to figure out what was going on. So it's like, oh, wait. Yes. Embarazada. Yeah, I'm sorry. See, I didn't, you know, I wrote it down right on my tweet because I copied it off of the screen. So but yeah, that's yeah.
I'm assuming
If you watch the show,
pregnant.
it was Catalina. I don't know if you ever saw that show, Grandma. Anyway, that's how bad I am with reality TV. So I
I failed Spanish in high school.
Huh? It's that stupid show. They're all stupid.
No, I mean, what is it? What word you learning?
Oh, yeah, pregnant, yeah.
Oh, okay.
That's what I mean. They gave her this little thing, and then she went, and she.
Can you do the energy of the capacitor?
Energy of a capacitor in the presence of a dielectric, that one?
Yeah, I think that's the one that I had chosen. I don't remember.
All right, here we go. Woo! All right, let's go. A dielectric.
Oh, no, not this one.
No, not that one.
This one was this. Because you did this one. Okay. Let's do it.
Wait.
Do it.
Hold on. Which one? Which one were you? Which did you do?
I think it was 11, but I don't know.
Okay, which one? Number 55?
Yeah.
Oh, that one, okay. In the following, C is 2.170 microfarads and VAB is 100 volts. Charge of capacitor C1 is 150 microcoulombs and the charge on C3 is 450 microcoulombs. And it says what is the value of the capacitance C2 and what is the value of the capacitance C3. That's interesting. So normally what you would do is you would go through and say, well, let's find the equivalent capacitance and then break it down. You would find the charge on each thing after breaking it down. This case, it's a little reverse. They're doing a little reverse on you. They say, well, we've got these capacitors. I'm going to give you the charge on a couple of them and then ask you different information. There we go. Okay, so we got C1. This is 2.7 microfarads. And we have C2 down here. We don't know what C2 is. And now I'm going to go ahead and draw C3 over here. Hopefully everybody could see that this is that this diagram is equivalent to the other one. Okay, all I did was take the point B and move it over here. So I've got C2. I don't know what C2 is. And I also don't know what C3 is. So this is C2, and here's C3. What I do know is that the voltage between points A and B is 100 volts. Okay, the charge on capacitor C1 is 150 microcoulombs. And the charge on capacitor C3 is 450 microcoulombs. Okay, so the first question it asks, what is the capacitance C2? So what do I need to know to find the capacitance C2? If you think about it in terms of 100B, I have two formulas with capacitance in it. Okay? I've got the definition of capacitance, which is the capacitance is charge per voltage. And I've got the other one, which is kappa epsilon naught A over D. That one. All right. Well, if I look at this one here, I know nothing about any of that. Okay? So it has to be this one. So what I need to do is I need to find the charge on that capacitor and the voltage across that capacitor. Everybody see that? I need to find, if I can find the charge and the voltage, I can find capacitance. Okay, so, well, let's see. This one is in what with that one? These two are in what?
Parallel.
These two are in parallel. So what has to be